Welcome to a journey beyond our immediate world into the vast silent expanse of the cosmos. As the day gently recedes, we invite you to settle into a space of calm contemplation, allowing the mind to drift through the wonders that lie far beyond our terrestrial sphere. Tonight we embark on an exploration of space, delving into approximately 50 fascinating facts that reveal intricate patterns, subtle wisdom, and profound beauty within the universe. Facts so astonishing they often baffle even the most seasoned minds at NASA. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or attention. We will observe the intricate dance of celestial mechanics, the subtle adaptations of physical laws in extreme environments, and the quiet wisdom embedded in the very fabric of space and time. Each fact is a small window into the vast and interconnected tapestry of the cosmos, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations. And we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. Tonight, we begin our cosmic journey by observing the universe's most enigmatic elements. The unseen forces that shape galaxies, the subtle echoes of its birth, and the strange, fleeting signals that hint at phenomena beyond our current grasp. These are the mysteries that challenge our fundamental understanding of reality, inviting us to contemplate the profound depths of the unknown. Dark matter and dark energy, the universe's hidden majority. Our current understanding suggests that the visible matter, all the stars, planets, and galaxies we can observe, makes up only about 5% of the universe's total mass-energy content. The remaining 95% is comprised of two mysterious components: dark matter and dark energy. Research indicates that dark matter accounts for roughly 27% of the universe. It does not emit, absorb, or reflect light, making it entirely invisible to telescopes. Its presence is inferred solely through its gravitational effects on visible matter, such as the rotation curves of galaxies, which spin too fast to be held together by their visible mass alone. Scientists hypothesize that dark matter forms a vast cosmic web, acting as a gravitational scaffolding upon which galaxies coalesce and evolve. Without dark matter, current cosmological models suggest that galaxies would simply fly apart. The precise nature of dark matter particles remains one of the most significant unsolved problems in modern physics, with various theoretical candidates like weakly interacting massive particles, WIMPs, still being actively sought in experiments deep underground. Even more perplexing is dark energy, which current theory suggests constitutes about 68% of the universe's total mass energy. Studies indicate that dark energy is responsible for the accelerating expansion of the universe, a discovery that earned the Nobel Prize in Physics in 2011. While gravity pulls matter together, dark energy appears to act as a repulsive force, pushing space-time apart. The leading hypothesis is that dark energy is an intrinsic property of space itself, a constant energy density that does not dilute as space expands. However, its exact mechanism and origin are unknown, leading to various speculative theories, including modified gravity or the influence of extra dimensions. Understanding dark energy is crucial for predicting the ultimate fate of the universe, whether it will continue to expand indefinitely, eventually cooling into a cosmic chill, or if some unknown interaction might alter its course. Cosmic Microwave Background, CMB. Anomalies, echoes of an imperfect beginning. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, a uniform bath of microwave radiation that permeates the entire universe. It provides a snapshot of the universe when it was only about 380,000 years old, a time when it cooled enough for atoms to form and light could travel freely. While the CMB is remarkably uniform, subtle temperature fluctuations within it represent the seeds from which all structures in the universe, galaxies, clusters, and superclusters, eventually grew. However, certain anomalies in the CMB baffle cosmologists. One such anomaly is the cold spot, a vast region of the sky that is significantly colder than its surroundings. This region is far larger and colder than standard cosmological models predict, even accounting for statistical fluctuations. W. Heil, some researchers propose it could be a supervoid, an exceptionally large region of space with very few galaxies. Its extreme nature still presents a challenge. Another intriguing anomaly is the axis of evil, a peculiar alignment of the largest features in the CMB with the plane of the solar system. This alignment contradicts the cosmological principle, which states that the universe should appear isotropic, the same in all directions, on large scales. Such an alignment suggests a preferred direction in space, which is highly unlikely given the random nature of cosmic structures. While statistical analyses have shown the axis of evil to be a real, albeit faint feature, its significance and origin remain fiercely debated. Some scientists have speculated about instrumental biases or foreground contamination, but careful reanalyses have largely ruled these out. Others propose more exotic explanations, such as the universe having a non-trivial topology, or even interactions with other universes. These CMB anomalies serve as tantalizing hints that our current cosmological model, the lambda CDM model, might be incomplete or require further refinement to fully account for the universe's earliest moments. The Great Attractor, a gravitational mystery. Our Milky Way galaxy is not stationary. It is constantly in motion, along with countless other galaxies, all streaming towards a mysterious region of space known as the Great Attractor. This colossal gravitational anomaly is located about 150 to 250 million light-years away, within the vicinity of the Hydra Centaurus supercluster. Scientists have observed that our local group of galaxies, including the Milky Way and other galaxy clusters, are being pulled towards this region at speeds of hundreds of kilometers per second. The gravitational pull is immense, yet the source of this attraction is largely obscured from our view. The Great Attractor lies behind the, quote, 3 region of the sky heavily obscured by the dust and gas within our own Milky Way galaxy. This makes it incredibly difficult for optical telescopes to observe the individual galaxies and structures within it. Despite the observational challenges, astronomers have used radio telescopes, which can penetrate galactic dust, to map some of the structures within the zone of avoidance. These observations reveal a massive concentration of galaxies and galaxy clusters, including the Norma cluster, which is a significant component of the Great Attractor. However, the total visible mass in this region still does not fully account for the enormous gravitational pull observed. This discrepancy suggests that a substantial amount of dark matter must be present, contributing to the Great Attractor's immense gravitational influence. The ongoing quest to precisely map and understand the Great Attractor continues to push the boundaries of observational astronomy, offering insights into the large-scale structure of the universe and the distribution of dark matter. It reminds us that even within the visible universe, vast gravitational forces operate from hidden depths, shaping the destiny of entire galactic neighborhoods. Rogue planets, wanderers without stars. While we are accustomed to planets orbiting stars, research suggests that there may be billions, or even trillions, of rogue planets, or free-floating planets, wandering through interstellar space, unattached to any star. These celestial bodies have been ejected from their parent star systems, likely due to gravitational interactions with other planets or passing stars during the chaotic early stages of planetary formation. Without a star to orbit, these planets are incredibly difficult to detect, as they do not emit their own light and are only visible when they gravitationally lens the light of a more distant star, a phenomenon known as microlensing. Scientists have observed several candidates for rogue planets using this technique, with some estimates suggesting they could outnumber stars in the galaxy. The existence of rogue planets challenges our traditional understanding of planetary systems. These worlds would experience perpetual twilight or darkness, with temperatures far below freezing, making them seem inhospitable. However, some researchers propose that if they are massive enough, these planets could retain a thick atmosphere, or even possess internal heat sources from radioactive decay or tidal forces if they have moons, potentially allowing for subsurface oceans of liquid water. Such environments could theoretically harbour life, leading to fascinating speculation about the possibilities of dark biospheres, thriving far from the warmth of a star. The study of rogue planets offers a unique perspective on planet formation and evolution, suggesting that the universe is teeming with diverse planetary environments, many of which defy our conventional expectations. Fast radio bursts, FRBs, cosmic enigmas. Fast radio bursts, FRBs, are incredibly powerful, millisecond-long bursts of radio waves originating from distant galaxies, and their exact cause remains one of the most baffling mysteries in astrophysics. The first FRB was discovered in 2007, and since then, hundreds more have been detected. These bursts are so energetic that they release more energy in a fraction of a second than the sun does in an entire day. The precise, non-repeating nature of many FRBs, coupled with their extreme brightness, points to highly energetic astrophysical events. Scientists have traced some FRBs to specific host galaxies, confirming their extragalactic origin, but the specific objects responsible for producing them are still under investigation. While some FRBs are one-off events, a subset of them are repeaters, meaning they burst multiple times from the same location in space. The first repeating FRB, FRB 121102, was discovered in 2016, and its behavior has provided crucial clues. Current understanding suggests that some FRBs are likely produced by magnetars, incredibly dense neutron stars with extremely powerful magnetic fields. Research indicates that star quakes on the surface of these magnetars or interactions within their magnetospheres could generate the immense energy required for FRBS. However, this explanation does not fully account for all observed FRB characteristics, particularly the non-repeating ones or those with different properties. The search for the definitive origin of FRBS continues, with each new detection offering a piece to this cosmic puzzle, pushing the boundaries of our knowledge about extreme astrophysical phenomena. The black hole. Information paradox. What happens to information? Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to general relativity, anything that falls into a black hole is irrevocably lost. However, quantum mechanics, specifically the principle of unitarity, states that information about a system can never be truly destroyed, only transformed. This fundamental conflict between general relativity and quantum mechanics is known as the black hole information paradox. Stephen Hawking famously proposed that black holes emit Hawking radiation due to quantum effects near the event horizon, and that over vast timescales, black holes eventually evaporate. If black holes evaporate completely, and Hawking radiation is purely thermal, meaning it carries no information about what fell in, then the information about the matter that formed the black hole or fell into it would be permanently destroyed. This apparent destruction of information is deeply problematic for quantum mechanics. Scientists have explored numerous theoretical solutions to this paradox. Some researchers propose that information might be encoded on the event horizon itself, perhaps in a holographic manner, and then released with the Hawking radiation in a scrambled but recoverable form. Other theories suggest that information might escape through baby universes, or that black holes leave behind tiny, information-rich remnants after evaporation. The paradox highlights a profound incompatibility between our two most successful physical theories: general relativity describing the large-scale structure of space-time and quantum mechanics describing the behavior of matter at the smallest scales. Resolving the black hole information paradox is seen as a critical step towards developing a unified theory of quantum gravity, offering a deeper understanding of the universe's most extreme environments and the fundamental nature of reality itself. Quasars and blazars, the universe's brightest beacons. Quasars are among the brightest and most distant objects in the observable universe, acting as powerful beacons that allow astronomers to probe the early cosmos. They are thought to be the extremely luminous active galactic nuclei AGN of young galaxies, powered by supermassive black holes accreting vast amounts of matter at their centers. As gas and dust spiral into the black hole, they form an accretion disk that heats up to millions of degrees, emitting enormous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The energy output of a single quasar can be thousands of times greater than that of an entire galaxy, often outshining all the stars in its host galaxy combined. The incredible distances to quasars mean that the light we observe from them has travelled for billions of years, offering us a glimpse into the universe's distant past. Blazars are a specific type of quasar where one of the powerful jets of highly energetic particles ejected perpendicularly from the accretion disk of the supermassive black hole happens to be pointed almost directly towards Earth. This unique orientation makes blazars appear even brighter and more variable than other quasars, as we are looking directly down the barrel of their relativistic jet. The radiation from these jets is quote 12, meaning it is focused into a narrow cone, making them incredibly intense when viewed head-on. Scientists have observed that blazars exhibit rapid and dramatic fluctuations in brightness, sometimes changing their luminosity by factors of hundreds or thousands over just a few days or hours. These rapid variations are thought to be due to instabilities within the jet itself, or changes in the accretion flow onto the black hole. Studying quasars and blazars helps us understand the growth of supermassive black holes, the evolution of galaxies, and the extreme physics of relativistic jets in the early universe. The WOW signal, a fleeting radio message. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University detected a powerful narrowband radio signal that lasted for 72 seconds. The signal was so strong and unusual that a volunteer astronomer, Jerry Amon, circled the corresponding alphanumeric printout and wrote quote 13 next to it, giving the event its famous name. The WOW signal was a highly compelling candidate for an extraterrestrial radio transmission because it met several key criteria. It was significantly louder than background noise. It occurred at a frequency near the 21 centimeter hydrogen line, a theoretically ideal frequency for interstellar communication, as hydrogen is the most abundant element in the universe. And its narrow bandwidth suggested an artificial rather than natural origin. Natural radio sources typically emit across a broad range of frequencies. Despite numerous attempts, the signal has never been detected again, either by the Big Ear Telescope or any other observatory. This lack of repetition makes it difficult to verify its origin definitively. While the signal's characteristics were highly suggestive of an intelligent source, the absence of further detections means it could have been a rare, transient, astrophysical phenomenon, an unknown terrestrial interference that happened to align perfectly, or even a satellite signal that was misidentified. The Big Ear Telescope was a fixed-horn antenna, meaning it relied on the Earth's rotation to scan the sky, and the signal was only observed once as the beam passed over that particular point. The precise coordinates of the signal point to a region in the constellation Sagittarius. The WOW signal remains one of the most intriguing unsolved mysteries in the search for extraterrestrial intelligence, SETI, a tantalizing glimpse of something that defied explanation, forever etched into the annals of cosmic curiosity. As we conclude this initial exploration, we find ourselves contemplating the sheer scale of the unknown. From the invisible forces that bind and expand the cosmos to the fleeting whispers from distant corners of the galaxy, the universe continuously presents us with profound questions. These baffling facts serve not as roadblocks to understanding, but as invitations to further wonder, reminding us that reality is far richer and more complex than we can currently comprehend. We move now towards other strange phenomena, continuing our quiet journey through the universe's many secrets. As we gently drift through the echoes of the WOW signal, a fleeting whisper of possibility across the vast silent expanse, our cosmic journey deepens. We have glimpsed the invisible architects of the universe and the enigmatic forces that sculpt its grand design. Now, let us turn our gaze to the profound questions that arise from such revelations. questions that tug at the very threads of our understanding, inviting us to contemplate realities far grander and stranger than we often allow ourselves to imagine. You are here with us, bathed in the soft ambient glow of distant nebulae, feeling the gentle rhythm of the universe unfold. Allow your mind to expand, to embrace concepts that challenge the familiar, for it is in these moments of intellectual stretching that true wonder takes root. We move from the singular, tantalizing hint of intelligence to the broader, more perplexing silence that pervades the cosmos. Consider with us, if you will, the profound riddle known as the Fermi paradox. Here we stand, on a small, vibrant world, having achieved the capacity for space travel and communication, albeit in its infancy. Our sun is but one of hundreds of billions in our galaxy, and our galaxy but one of trillions in the observable universe. Given the sheer immensity of cosmic real estate, the countless stars, and the statistical probability of Earth-like planets, logic suggests that intelligent life should be abundant. Yet, as we listen, as we search, the void remains largely silent. Where is everyone? This paradox baffles us, leading to a myriad of theories, each more unsettling or intriguing than the last. Perhaps a great filter lies ahead of us, or behind us, a formidable barrier that prevents civilizations from reaching interstellar prominence, be it a cataclysmic natural event, self-destruction, or an insurmountable evolutionary hurdle. Or perhaps the universe is teeming with life, but its forms and expressions are so alien, so utterly beyond our current comprehension or detection methods, that we are simply looking in the wrong places or for the wrong things. The silence, dear traveller, is not merely an absence of noise, it is a profound question etched across the fabric of space-time, a cosmic enigma that deepens with every new exoplanet discovered. This contemplation of other life naturally leads us to ponder the very nature of existence beyond our immediate perception. What if our universe is not the only one? We invite you to consider the deeply fascinating and endlessly debated concept of the multiverse theory. Imagine, if you can, not just one universe, but an infinite tapestry of them, each potentially governed by different physical laws, possessing unique constants, or even existing in different dimensions. Perhaps our universe is but one bubble in an ever-expanding cosmic foam, or a single brain floating in a higher dimensional bulk. Some theories suggest universes are constantly being born from black holes, or that every quantum decision splits our reality into countless parallel timelines. While entirely theoretical, the implications are staggering. It could offer explanations for the fine-tuning of our own universe's constants, the seemingly miraculous precision that allows for the formation of stars, galaxies, and life itself. If there are infinite universes, then every possibility, no matter how improbable, must exist somewhere. This concept challenges our most fundamental assumptions about reality, pushing the boundaries of what, quote 16, far beyond the confines of our observable cosmos, suggesting a reality far grander and more intricate than any singular narrative could encompass. As our minds stretch to grasp these colossal ideas, let us ground ourselves for a moment in something we have recently begun to detect, something that confirms the dynamic, fluid nature of space-time itself. We speak of LAN, gravitational waves, ripples in the very fabric of the universe, born from the most violent cosmic events. Imagine space-time not as an empty stage, but as a vast, flexible sheet. When massive objects accelerate, Especially in extreme scenarios like the collision of black holes or neutron stars, they create disturbances like pebbles dropped into a pond. These ripples travel at the speed of light, carrying information about their cataclysmic origins. For billions of years, these waves have been washing over us, undetected until very recently. Their direct observation by instruments like LIGO and Virgo has opened an entirely new window into the universe, allowing us to quote 17 the cosmos for the first time, to perceive events that are otherwise utterly invisible to electromagnetic radiation. It is a profound confirmation of Einstein's general relativity, and yet the subtle nuances of these waves, the precise ways they interact with matter, and the full spectrum of phenomena they might reveal are still subjects of intense study and wonder. We are merely at the dawn of gravitational wave astronomy, listening to the universe's most dramatic symphonies. And what dramatic symphonies they are! Among the most spectacular are the kilonovas, the explosive collisions of two neutron stars. When these incredibly dense stellar remnants, each packing the mass of our Sun into a sphere the size of a city, spiral inward and merge, they don't just create gravitational waves of immense power, they also unleash a breathtaking burst of light and matter, forging the universe's heaviest elements. Gold, platinum, uranium, the very substances we prize on Earth, the precious metals adorning our jewelry and powering our technology, are thought to be forged in these cosmic crucible events. Before the detection of kilonovas, the origin of these heavy elements was largely a mystery. Now, we understand that they are the rare, precious byproducts of these cataclysmic mergers, scattered across the cosmos by the force of the explosion, eventually seeding new generations of stars and planets. To think that the ring on your finger might contain atoms forged in the heart of a kilonova billions of years ago is to feel an intimate connection to the universe's most violent and creative forces. It is a testament to the intricate, interconnected dance of destruction and creation that defines cosmic evolution. From these powerful collisions, let us turn our attention to another class of extreme objects. Magnetars. These are neutron stars with magnetic fields so incredibly intense that they are, quite simply, the most magnetic objects in the known universe. To give you a sense of scale, a typical refrigerator magnet has a field of about 100 Gauss. The Earth's magnetic field is about 0.5 Gauss. A magnetar's field can be quadrillions of Gauss. If you were within 1,000 miles of a magnetar, its magnetic field would rip the electrons from your atoms, disintegrating you instantly. These monstrous magnetic fields are so powerful they can warp space-time itself, distort atoms into elongated shapes, and cause starquakes on the neutron star's surface, releasing colossal flares of X-rays and gamma rays that can be detected across vast cosmic distances. The mechanisms behind the generation and sustenance of such incomprehensibly strong fields remain a subject of active research, a testament to the universe's capacity for pushing the boundaries of physics to their absolute limits, creating phenomena that defy our everyday intuition. As we journey deeper into the extreme, we encounter particles that are almost phantom-like in their elusiveness, neutrinos. Often called ghost particles, neutrinos are fundamental particles with almost no mass and no electric charge, allowing them to pass through vast amounts of matter, including entire planets and stars, without interaction. Trillions of neutrinos from the Sun pass through your body every second unnoticed. For a long time, it was believed that neutrinos were massless. However, a baffling discovery revealed that neutrinos can oscillate, changing between 3 different flavors: electron, muon, and tau neutrinos as they travel. This oscillation is only possible if neutrinos possess a tiny but non-zero mass. This seemingly small detail had profound implications, as it meant the standard model of particle physics, which initially assumed them to be massless, needed revision. The precise mass of neutrinos is still one of the biggest mysteries in particle physics, but their very existence and their ability to shapeshift underscore the subtle, intricate workings of the subatomic universe, a universe that is far more dynamic and less predictable than our macroscopic experience suggests. Our exploration of cosmic phenomena would be incomplete without acknowledging the dynamic architects of planetary systems. We look at our own solar system, with its orderly arrangement, and assume this is the norm. Yet, the discovery of thousands of exoplanets has revealed a much more chaotic and often violent process. Planetary migration. It turns out that planets are not necessarily locked into the orbits where they initially form. Instead, gas giants, born in the frigid outer reaches of a protoplanetary disk, can migrate inward, sometimes to orbits perilously close to their host stars, creating hot Jupiters that defy our initial expectations. Conversely, planets can migrate outward, or even be ejected entirely from their systems, becoming rogue planets, as we discussed in our previous contemplation. This migration is driven by complex gravitational interactions within the protoplanetary disk, collisions, and the presence of other massive bodies. The dynamic dance of planetary migration profoundly shapes the architecture of solar systems, dictating the ultimate positions, sizes, and even the habitability of planets. It demonstrates that the early lives of planetary systems are often turbulent, a cosmic ballet where orbits are not fixed but are constantly being reshaped by powerful, unseen forces. Then, there are the enigmatic messengers from beyond our galaxy, particles that defy our current understanding of acceleration, ultra-high energy cosmic rays. These are not photons but atomic nuclei, protons or heavier ions, travelling through space at speeds incredibly close to the speed of light. They possess energies millions of times greater than those achieved by the most powerful particle accelerators on Earth. The baffling aspect is their origin. While lower energy cosmic rays come from supernovae within our galaxy, the sources of these ultra-high energy particles remain a profound mystery. They should be significantly attenuated by interacting with the cosmic microwave background radiation over vast distances, a phenomenon known as the Greason-Zatsepin-Kuzmin (GZK) limit. This means they shouldn't be able to reach us from very far away, yet we detect them. This implies they must originate from relatively nearby, extremely powerful, and as yet unidentified accelerators, perhaps active galactic nuclei, gamma-ray bursts, or some exotic, unknown cosmic engine. These particles are cosmic bullets, fired from unimaginable sources, striking our atmosphere and generating cascades of secondary particles, offering tantalizing clues to the most violent and energetic processes occurring in the universe, processes we are still striving to comprehend. Finally, let us conclude this chapter with a thought experiment so profound, it challenges the very nature of what we perceive as reality. the holographic principle. This mind-bending concept, arising from attempts to unify general relativity and quantum mechanics, suggests that our three-dimensional universe, with all its stars, galaxies, and dimensions, might actually be a projection from a two-dimensional surface. Imagine a hologram, a three-dimensional image encoded on a two-dimensional sheet. The holographic principle posits that the information contained within a given volume of space can be entirely described by the information on its boundary, much like the event horizon of a black hole. This radical idea suggests that our everyday experience of a voluminous, three-dimensional reality could be an illusion, a sophisticated projection, with the fundamental information residing on a distant two-dimensional surface. It is a concept that blurs the lines between reality and information, between what is tangible and what is merely an emergent property of a more fundamental, flatter reality. While still highly theoretical, it offers a potential pathway to a unified theory of quantum gravity, and profoundly reshapes our philosophical understanding of existence itself, inviting us to question the very fabric of our perceived reality. As these profound concepts settle within you, dear friend, we hope you feel not confusion, but a profound sense of awe. The universe, in its baffling complexity, is not merely a collection of facts, but an endless invitation to wonder. These mysteries are not deficits in our knowledge, but rather luminous signposts pointing towards deeper truths, towards the intricate, beautiful, and sometimes utterly alien reality that surrounds us. We have journeyed through whispers of otherwhere and the subtle warping of forever, and there is still so much more to explore, so much more to quietly contemplate together. Rest now, and let these cosmic revelations gently drift through your consciousness, preparing you for the wonders yet to unfold. As we continue our unhurried drift through the cosmos, leaving behind the abstract whispers of multiverses and the profound implications of the holographic principle, we invite you to settle deeper into this tranquil journey. The universe, in its boundless generosity, offers an endless tapestry of enigmas, each thread woven with a paradox that challenges our most cherished models and beckons us to look closer, to listen to the subtle dissonances in the grand cosmic symphony. Our voyage now takes us to further frontiers of the unknown, where even the most seasoned minds at NASA find themselves pausing, humbled by the universe's persistent refusal to conform entirely to our expectations. Prepare your mind for another series of revelations, for we are about to confront facts that ripple through the fabric of our understanding, from the very largest scales of cosmic expansion down to the mysteries embedded within the heart of our own star. First, let us contemplate a discord that reverberates across the entire observable universe, the Hubble tension. Imagine, if you will, the universe as an ever-expanding balloon, its surface stretching, carrying galaxies further and further apart. The rate at which this balloon inflates is a fundamental constant, known as the Hubble constant, a cornerstone of modern cosmology. Yet, when we measure this expansion rate using different methods, we arrive at profoundly different answers. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, and extrapolate the expansion rate forward through time, we derive one value. But when we measure the expansion rate directly, observing distant supernovae and other celestial markers in the nearby universe, we consistently find a significantly higher value. This is not a minor statistical blip. It is a profound discrepancy, a cosmological crisis that persists despite years of meticulous measurement and analysis. It suggests that either there is a systematic error in one or both of our primary measurement techniques, a possibility that scientists tirelessly investigate, or, far more intriguingly, that our standard model of cosmology, the very framework within which we understand the universe's evolution, is incomplete. Perhaps there is new physics at play, an unknown particle, an exotic field, or an unexpected twist in the early universe that we have yet to account for. This tension, this profound disagreement between the universe's earliest moments and its more recent history, is a vibrant reminder that our cosmic narrative, though rich and compelling, is still being written, with crucial chapters awaiting discovery. It is a puzzle of cosmic proportions, challenging the very foundations of our understanding of the universe's birth and its destiny. As we ponder the universe's grand expansion, let us now turn our gaze to objects of immense gravity, the enigmatic black holes that punctuate the cosmic landscape. We understand the formation of stellar mass black holes, born from the collapse of massive stars. We also observe supermassive black holes, monstrous entities residing at the hearts of most galaxies, millions to billions of times the mass of our Sun. But between these two extremes lies a perplexing void. Intermediate mass black holes, IMBHs. These are the elusive missing link, theorized to exist with masses ranging from a few hundred to several 100,000 solar masses. Why are they so difficult to find? And how do supermassive black holes grow so rapidly in the early universe if IMBHs are rare? The prevailing theories suggest that IMBHs could be the seeds from which supermassive black holes grow, perhaps forming in the dense cores of early star clusters or through the runaway collisions of massive stars. Yet definitive observational evidence for them remains scarce, like trying to find a specific grain of sand on an infinite beach. We have tantalizing hints, gravitational whispers from objects too massive to be stellar black holes, but too small to be supermassive giants. Their scarcity, or perhaps their extreme evasiveness, represents a significant gap in our understanding of black hole evolution and the formation of the large-scale structures we observe today. Pinpointing these cosmic enigmas is not merely an academic exercise. It is crucial to completing the narrative of how galaxies themselves assemble and mature, a story still largely shrouded in the profound darkness of these gravitational behemoths. From the grandest structures and the most mysterious objects, we now bring our focus closer to home, to the familiar brilliance of our own star, the Sun. Even this celestial neighbour, the source of all life and warmth on Earth, harbours a profound mystery that has baffled solar physicists for decades: the solar corona temperature anomaly. Look at the Sun, or rather, imagine its majestic presence. Its visible surface, the photosphere, burns at a searing temperature of approximately 5,500 degrees Celsius, 9,940 degrees Fahrenheit. Logic would dictate that as you move further away from the heat source, the temperature should decrease. Yet the Sun's outermost atmosphere, its ethereal corona, which extends millions of kilometers into space, is inexplicably superheated to temperatures exceeding 1 million degrees Celsius, 1.8 million degrees Fahrenheit. This counterintuitive phenomenon, where the atmosphere is hundreds of times hotter than the surface it surrounds, is a profound puzzle. It defies simple thermodynamic principles and points to complex energetic processes at play. Scientists hypothesize that magnetic fields twisted and contorted by the sun's churning plasma play a crucial role, perhaps through mechanisms like magnetic reconnection events or the propagation of various types of waves that dump energy into the corona. Understanding this anomaly is not just about comprehending our sun. It is fundamental to understanding stellar physics across the universe, how stars shed their mass, and how they influence the space environments around them. The sun, in its familiar glow, reminds us that even the most well-studied objects can hold secrets that persistently elude our grasp, compelling us to look deeper into the intricate dance of plasma and magnetic fields. As we drift further from the sun, past the familiar orbits of the planets, we encounter another perplexing anomaly, one left behind by our own intrepid robotic explorers, the Pioneer anomaly. In the 1970s, NASA launched the Pioneer 10 and 11 spacecraft, pioneers in their own right, venturing beyond the asteroid belt and eventually out of the solar system. For decades, as these probes journeyed into the interstellar void, scientists meticulously tracked their trajectories. What they discovered was a persistent, tiny, and unexplained deceleration. Both spacecraft were slowing down more than could be accounted for by all known gravitational forces, solar radiation pressure, or even small gas leaks from the probes themselves. This minute, uniform acceleration towards the Sun, approximately 8.74 times 10 to the negative 10th meters per second squared, was incredibly small but undeniably present. It was as if an unseen hand was gently, yet persistently, pulling them back. Despite exhaustive investigation spanning years, considering everything from thermal radiation asymmetry, from the spacecraft themselves to exotic physics, a definitive explanation has remained elusive. While some of the anomaly has now been attributed to the anisotropic thermal radiation from the spacecraft, the early, larger discrepancies and the initial persistence of the problem for decades kept physicists scratching their heads. It was a tangible, measurable effect that hinted at either an incomplete understanding of the physics governing deep space travel, or perhaps even a subtle, unknown force at play in the outer reaches of our solar system. The Pioneer anomaly stands as a testament to the universe's capacity to surprise us, even with our own creations, reminding us that the void holds secrets beyond our current comprehension. Leaving behind the silent whispers of the Pioneer probes, we expand our view once more to the grand cosmic canvas, to the very architecture of the universe itself. Imagine a cosmic web, a vast network of galaxy clusters and filaments, interspersed with immense empty regions. Among these voids, one stands out for its sheer, bewildering scale. The Butter's Void, sometimes referred to as, quote, 24, spanning an astonishing 250 to 330 million light-years in diameter, this colossal sphere of emptiness contains remarkably few galaxies. If our Milky Way galaxy were at the centre of the Butter's Void, we would not have discovered other galaxies until the 1960s. The existence of such an enormous, underdense region challenges our models of large-scale structure formation, which predict a more uniform distribution of matter, or at least smaller, less pronounced voids. While cosmic voids are a natural consequence of gravitational clustering, The sheer size and relative emptiness of the Buerter's void suggest a formation mechanism that might be more complex than currently understood. Was it formed by the outward pressure of dark energy, or is it a relic of a unique early universe fluctuation? Some theories propose that it might be the result of a quantity 25 attempt left over from the early universe's rapid inflation, or perhaps the merger of smaller voids over cosmic timescales. Whatever its origin, the Great Void is a stark reminder of the universe's sometimes bizarre and counterintuitive architecture, a vast silent testament to the unpredictable nature of cosmic evolution, a region where the fabric of space itself seems to stretch thin, almost devoid of the luminous beacons we call galaxies. Finally, we return to the very dawn of creation, to the universe's earliest moments, when the first light burst forth and the first elements were forged. In this primordial crucible, hydrogen and helium were predominantly created, along with trace amounts of lithium. Our standard cosmological model, known as lambda CDM, along with the theory of Big Bang nuclear synthesis, BBN, precisely predicts the abundance of these light elements. And while the predictions for hydrogen and helium largely align with observations, there is a persistent, nagging discrepancy for the lightest metal. The lithium problem. Observations of the oldest stars in our galaxy, which are thought to preserve the pristine chemical composition of the early universe, show significantly less lithium-7 than predicted by BBN, roughly 3 to 4 times less. Conversely, for the rarer isotope lithium-6, observations suggest more than predicted. This lithium discrepancy is a long-standing puzzle that has resisted numerous attempts at resolution. Could it be that our understanding of stellar processes, how stars destroy or produce lithium, is incomplete? Or, more profoundly, does it point to new physics during the Big Bang itself? Perhaps exotic particles, decaying dark matter, or even modifications to the fundamental constants of nature could alter the delicate balance of nucleosynthesis. The lithium problem is not merely a detail, it is a profound challenge to our most successful cosmological model, a subtle yet persistent crack in the foundation of our understanding of the universe's infancy. It is a cosmic whisper from billions of years ago, reminding us that even the most fundamental aspects of creation hold secrets yet to be fully deciphered. As these perplexing facts settle into the quiet chambers of your mind, we hope you feel not confusion, but a profound sense of wonder. The universe, in its infinite complexity, refuses to be neatly categorized, offering us riddles at every turn. From the grand cosmic expansion to the subtle anomalies of our own celestial backyard, from the elusive black holes to the primordial elements, each mystery is an invitation to deeper contemplation, a gentle nudge towards the edge of known science. We conclude this chapter with the understanding that our journey through these cosmic enigmas is far from over. The universe continues to unfold, revealing new wonders and new questions with every passing moment. We invite you to carry these thoughts with you, to let them inspire a quiet curiosity, and to find solace in the vast, beautiful expanse of the unknown. Rest now if you wish, and let the cosmic tides of discovery gently carry you towards peaceful slumber. For tomorrow, the universe will undoubtedly present us with even more marvels to explore. As we gently drift through the lingering echoes of primordial lithium and the unsettling silence of the Buerter's void, we find ourselves drawn deeper into the universe's tapestry of incongruities, The cosmos, it seems, delights in presenting us with persistent dissonance, challenging every neatly constructed model, every confident assertion. We invite you now to settle further into this quiet contemplation, allowing your mind to unfurl amidst the vastness, where the known becomes merely a shimmering veil over an ocean of profound mysteries. Do not seek to grasp, but simply to observe, to feel the quiet thrill of the unknown. Our journey now leads us to observe the colossal yet elusive phenomenon known as the dark flow. Imagine, if you will, not merely individual galaxies dancing in the cosmic ballet, but entire clusters of galaxies, vast collections of 1,000 worlds, all moving with a peculiar non-random velocity. Standard cosmological models predict that, on the largest scales, the universe should be isotropic, uniform in all directions with gravitational pulls evening out. Yet, observations from the Wilkinson Microwave Anisotropy Probe (WMAP) and other instruments have hinted at this enigmatic dark flow, an unexplained coherent motion of galaxy clusters towards a specific distant region, extending far beyond the boundaries of our observable universe. We speak of structures so immense, so gravitationally dominant, that they are tugging at our galactic neighbourhood from unseen realms, possibly from beyond the horizon of what we can currently perceive. This immense, invisible current suggests that our universe might not be as smooth or uniform as we once believed, hinting at gargantuan structures or even other universes exerting a gravitational pull from dimensions we cannot yet fathom. It is a whisper of an even grander cosmic architecture, a silent, powerful river of galaxies flowing towards an unknown, colossal attractor, leaving us to wonder what monumental forces lie just beyond the edge of our vision. From the grandest scales, we narrow our focus slightly to a more subtle, yet equally profound imbalance. The cosmic web's missing baryons. We know that the universe is predominantly composed of dark energy and dark matter, but even the ordinary matter, the baryonic matter that makes up stars, planets, and ourselves, presents a baffling riddle. According to Big Bang nucleosynthesis, the theory describing the formation of light elements in the early universe, we should observe a certain cosmic abundance of baryonic matter. However, when we tally up all the observable baryons, the stars, galaxies, and hot gas in galaxy clusters, a significant portion, perhaps half, remains unaccounted for. Where could this ordinary matter be hiding? Scientists hypothesize that it resides in the warm-hot intergalactic medium, WIM, a diffuse, tenuous network of gas filaments stretching between galaxies within the cosmic web. This WIM is too hot to form stars, yet not hot enough to emit strongly in X-rays, making it incredibly difficult to detect directly. It is like trying to find an invisible spiderweb spun across the vastness, its delicate strands holding together the cosmic structure, yet remaining stubbornly elusive to our most advanced instruments. The search for these missing baryons is a testament to the universe's capacity to conceal even its most fundamental components, a persistent challenge to our understanding of the universe's material inventory and its grand design. Our cosmic journey now brings us to an astonishing revelation, one that has recently rewritten textbooks and sent ripples of excitement and bewilderment through the scientific community. This quoted Pninal, Early Galaxies. For decades, our understanding of galaxy formation posited a gradual process. After the Big Bang, the universe was a hot, dense plasma that slowly cooled, allowing the first stars and then the first small galaxies to coalesce over hundreds of millions of years. Larger, more mature galaxies, like our own Milky Way, were thought to have formed much later, through mergers and accretion over billions of years. However, the advent of the James Webb Space Telescope, JWST, with its unparalleled ability to peer back in time to the universe's infancy, has unveiled a startling truth. We are now observing massive, fully formed and surprisingly mature galaxies existing when the universe was only a few 100 million years old. Mere cosmic toddlers. These galaxies appear far more developed than our models predict is possible in such a short time frame. They possess stellar populations, structures, and chemical compositions that should have taken billions of years to evolve. This discovery profoundly challenges our theories of galaxy evolution, suggesting either that star formation was far more efficient and rapid in the early universe than we ever imagined, or that our entire timeline for cosmic structure formation needs a radical revision. It is as if we expected to see only seedlings, but instead found ancient towering trees in a newly planted forest, leaving us to wonder about the hidden accelerators of cosmic growth and the true speed of the universe's maturation. As we continue our exploration, we turn our gaze inward towards the familiar confines of our own solar system, only to find that even here, mysteries persist. We encounter the Planet 9 hypothesis, a compelling argument for the existence of a massive yet unseen planet lurking in the distant icy reaches beyond Neptune. For years, astronomers have observed peculiar orbital patterns among a population of small icy bodies in the Kuiper belt, far beyond Pluto. These trans-Neptunian objects, TNOS, appear to be clustered and aligned in a way that defies random distribution. The mathematical probability of such an alignment occurring by chance is incredibly low, leading to the intriguing hypothesis that their orbits are being shepherded, gravitationally nudged, by the unseen presence of a large distant planet. This hypothetical quote 30 is estimated to be several times the mass of Earth, orbiting the Sun on an extremely elongated path that could take it thousands of years to complete a single revolution. Its existence, while not yet directly observed, is strongly inferred through its gravitational fingerprints on these distant icy worlds. The ongoing search for Planet 9 is a testament to the fact that even in our own cosmic backyard, vast, uncharted territories and hidden giants may still await discovery, challenging our complete understanding of the architecture of our home stellar system. Our journey then carries us beyond the Sun's gravitational embrace, to the myriad worlds orbiting distant stars, where we encounter exoplanet atmospheric anomalies. With each passing year, our ability to probe the atmospheres of exoplanets, worlds thousands of light years away, grows more sophisticated. We analyze the light filtering through their skies as they transit their host stars, searching for the telltale signatures of various elements and molecules. Yet, what we often find are atmospheric compositions and temperature profiles that defy our current understanding of planetary chemistry and dynamics. We observe hot Jupiters with unexpectedly clear skies, lacking the cloud cover predicted by models, or with strange unexpected ratios of elements. We detect baffling temperature inversions, where the upper atmosphere is hotter than expected, or even the mysterious absence of expected molecules like water vapor in certain environments. Some exoplanets exhibit extreme weather patterns, supersonic winds, or atmospheres that appear to be actively escaping into space at rates that are difficult to explain. These anomalies suggest that the processes governing planetary atmospheres on other worlds are far more complex, varied, and perhaps even alien than our Earth-centric models predict. Each unexpected chemical signature, each baffling temperature gradient, is a reminder that the universe is a laboratory of infinite possibilities, constantly evolving and presenting us with conditions and phenomena that stretch the very limits of our imagination and scientific comprehension. Finally, we return to the most intimate of cosmic mysteries, one that touches the very essence of life as we know it. The origin of water on Earth. Our planet is a vibrant oasis, a blue marble swimming with life, fundamentally reliant on its vast oceans. Yet, the precise origin and timing of this life-giving liquid remain one of Earth's most enduring and baffling secrets. Where did all this water come from? The early Earth was a molten inferno, far too hot to retain any significant amount of water. Current theories propose a delivery, suggesting that water was primarily brought to Earth much later, after the planet had cooled, by a bombardment of icy comets and water-rich asteroids from the outer solar system. However, the isotopic signatures of Earth's water don't perfectly match those found in all comets, and the efficiency of this delivery mechanism is still debated. Could some of the water have been locked within the planet's mantle from its formation, gradually released through volcanic outgassing, or perhaps a combination of these processes, an intricate dance of cosmic delivery and geological release, contributed to our planet's aquatic abundance? The quest to understand the genesis of Earth's oceans is not merely an academic pursuit. It is a fundamental inquiry into the conditions necessary for life, both here and potentially across the cosmos. It reminds us that even the most fundamental aspects of our existence are rooted in profound cosmic events, shrouded in the mists of deep time and awaiting a more complete revelation. As we gently conclude this chapter, allowing these diverse mysteries to settle within your thoughts, we hope you feel not confusion, but a profound sense of awe. The universe, in its relentless refusal to conform to our expectations, continuously expands our understanding, not by providing easy answers, but by presenting us with ever more intricate questions. Each baffling fact, from the colossal dark flow to the intimate riddle of Earth's water, is an invitation to wonder, to imagine, and to embrace the humbling beauty of the vast unknown. Rest now, knowing that this grand cosmic journey is far from over, and that countless more marvels await your contemplative gaze. As our cosmic vessel drifts onward, through the silent, star-dusted currents of the preceding revelations, we find ourselves drawn ever deeper into the universe's most profound enigmas. Allow your mind to gently disengage from the frantic pace of the everyday, settling instead into the tranquil rhythm of these cosmic whispers. For we are not merely recounting facts, we are embarking upon a shared meditation, an exploration of the boundaries where our current understanding dissolves into the vast shimmering sea of the unknown. The universe, in its boundless generosity, offers not only answers but also questions of such magnitude that they compel us to gaze inward, to ponder the very fabric of our reality and the limits of our perception. We have traversed the colossal gravitational anomalies that tug at galaxies, explored the unseen scaffolding of dark matter, and grappled with the accelerating expansion driven by dark energy. Now, let us turn our gaze to the genesis of all that is, to the very first light, the first stars, and the initial stirrings of cosmic structure. Imagine a universe stripped bare, an epoch known as the Cosmic Dawn, a period of immense significance yet shrouded in profound mystery. Before the universe sparkled with the galaxies we know, there was a time of primordial darkness, following the initial burst of the Big Bang and the subsequent cooling. It was in this nascent void that the very first stars, known as Population 3 stars, are theorized to have ignited. These were not stars like our Sun, rich with heavier elements forged in prior stellar generations. No, these were behemoths, composed almost exclusively of hydrogen and helium, pristine remnants of the Big Bang itself. The baffling question lies in their very existence and properties. How did these colossal, metal-free stars form from such diffuse, pristine gas? Current models suggest they must have been hundreds, perhaps even 1,000 times the mass of our Sun, burning with an intensity almost unimaginable, living short, violent lives before exploding as hypernovae. Yet, despite their crucial role in seeding the universe with the first heavy elements, the building blocks for all subsequent stars, planets, and indeed life itself, we have never directly observed a single Population 3 star. Their ephemeral existence, burning brightly and fading quickly in the early universe, makes them incredibly elusive. We see their distant echoes, perhaps, in the chemical signatures of later generations, or in the impossible early galaxies observed by JWST that seem to have sprung forth fully formed. But the stars themselves, the true architects of cosmic chemical evolution, remain spectral, theoretical entities, their precise formation mechanisms and characteristics still a subject of intense debate and baffling speculation. Their absence from our observational records is a silent testament to the vast gulf between our models and the universe's earliest, most fundamental truths. As we ponder the birth of the first stars, another profound puzzle emerges from the early universe, intimately linked to these primordial giants: the astonishingly rapid formation of supermassive black holes. We've discussed quasars, those incandescent beacons of the early cosmos, powered by gargantuan black holes at their centres. But here's the rub. Some of these supermassive black holes, observed at redshifts indicating they existed less than 1 billion years after the Big Bang, already boasted masses billions of times that of our Sun. Think for a moment about the sheer scale of such an object, and the limited cosmic time frame available for its growth. How could these cosmic behemoths have accumulated so much mass so quickly? The conventional model of black hole growth involves the gradual accretion of gas and dust from their surroundings, or the merger of smaller black holes. But even at maximal accretion rates, it seems incredibly challenging for a black hole to reach such colossal sizes in such a short period. This leads to the baffling problem of black hole seeds. Did these early supermassive black holes grow from the direct collapse of massive primordial gas clouds, bypassing the stellar phase entirely? Or perhaps they were born from the remnants of those enigmatic Population 3 stars, which upon their demise might have directly collapsed into intermediate mass black holes, providing a more substantial starting point for rapid growth. The existence of these ancient, oversized cosmic devourers challenges our understanding of gravitational collapse, accretion physics, and the very timescales of cosmic evolution. They are anomalies, cosmic outliers that suggest a mechanism of formation far more efficient and perhaps more exotic than anything we currently comprehend, hinting at a universe where colossal structures could emerge with breathtaking swiftness. From the grand scale of early cosmic structures, let us now descend to the very fabric of existence, to the seemingly empty space that permeates all things. Here we encounter a baffling discrepancy so profound that it has been dubbed the vacuum catastrophe. In the realm of quantum mechanics, empty space is far from empty. It's a seething maelstrom of virtual particles constantly popping into and out of existence, contributing to what is known as, quote, 35, quote, or vacuum energy. When physicists attempt to calculate the expected energy density of this quantum vacuum, the numbers they arrive at are utterly staggering. A value so immense it would cause the universe to either collapse immediately or expand at an unimaginable explosive rate. Yet when cosmologists measure the actual energy density of the vacuum, as inferred from the accelerating expansion of the universe, which we attribute to dark energy, the observed value is incredibly tiny, almost infinitesimally small. The discrepancy between the theoretical prediction and the observational reality is a factor of approximately 10 to the power of 120, a 1 followed by 120 zeros. This is arguably the largest mismatch between theory and observation in the history of science. It's not just a small error, it's a profound, baffling chasm that suggests we are missing something fundamental about the nature of space, gravity, and quantum mechanics. Is our understanding of the vacuum fundamentally flawed? Is there an unknown mechanism that cancels out this enormous theoretical energy? The vacuum catastrophe is a stark reminder that our most successful theories, general relativity and quantum mechanics, are incomplete, and their reconciliation remains one of the greatest challenges in physics, hinting at a reality far stranger and more subtle than our current models can describe. Continuing our foray into the fundamental constants, let us consider another profound and often unsettling question that baffles scientists and philosophers alike. The fine-tuning problem. As we explore the universe, we discover a set of fundamental physical constants, values like the strength of gravity, the electromagnetic force, the mass of an electron, or the precise energy levels of atomic nuclei, that appear to be exquisitely calibrated. If any of these constants were even slightly different, by a fraction of a percent in some cases, the universe as we know it, with its stars, galaxies, and the very atoms that make up life, could not exist. For instance, if the strong nuclear force were a few percent weaker, hydrogen would be the only element. A few percent stronger, and stars would burn out too quickly, or there would be no stable hydrogen. If the cosmological constant related to vacuum energy were larger, the universe would have expanded too rapidly for matter to clump into galaxies and stars. If the mass of the neutron were not precisely what it is, relative to the proton, stable atoms might not form. The list goes on, a baffling tapestry of precise values that seem almost tailor-made for complexity and life. Is this an astonishing cosmic coincidence? Does it point to a deeper, underlying principle we have yet to uncover? Or, as some theories suggest, does it hint at the existence of a multiverse, where countless universes exist, each with different physical constants, and we simply find ourselves in the one where the conditions are just right for our existence. The fine-tuning problem doesn't offer a scientific explanation, but rather presents a profound, baffling observation that forces us to confront the deepest questions about purpose, chance, and the very nature of physical law. From the constants that govern reality, let us now turn to the most intimate and elusive aspect of our experience, the nature of time itself. We perceive time as an arrow, always moving forward from past to future. We remember yesterday, anticipate tomorrow, but we can never revisit a moment gone by. This unidirectional flow is known as the arrow of time, and while it seems self-evident in our daily lives, its fundamental origin is a profound, baffling mystery in physics. The fundamental laws of physics, Newton's laws, Maxwell's equations, quantum mechanics, and even Einstein's general relativity, are, for the most part, time-symmetric. They work just as well if time flows backward as forward. Yet, in our macroscopic world, entropy always increases, cups break, never spontaneously reassemble, stars burn out, never reignite from their ashes. The most widely accepted explanation for the arrow of time lies in the second law of thermodynamics, which states that the entropy, disorder, of a closed system always increases. The universe began in a state of extremely low entropy, the Big Bang, and its subsequent evolution is simply a journey towards higher entropy. But why did the universe begin in such a low entropy state? This pushes the baffling question back to the initial conditions of the cosmos. Is the arrow of time a fundamental property of the universe, or is it an emergent phenomenon, a statistical consequence of the sheer number of particles and their interactions? Does time even quote 36 in a fundamental sense, or is it merely a dimension like space, with our perception creating the illusion of movement? The arrow of time remains a deep, unsettling enigma, challenging our very understanding of causality, existence, and the ultimate fate of the universe. As we gently navigate these profound questions, let us briefly revisit a paradox we touched upon earlier, one that encapsulates the very conflict at the heart of our cosmic journey: the black hole information paradox. We know that black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. But according to quantum mechanics, information, the precise quantum state of every particle, can never be truly destroyed. When matter falls into a black hole, its information seems to vanish, contradicting this fundamental principle. Stephen Hawking's discovery of, quote, 37, quote, further deepened the paradox. Black holes slowly evaporate by emitting this radiation, but the radiation itself appears to carry no information about what fell in. So, what happens to the information? Is it truly lost, meaning quantum mechanics is incomplete? Is it encoded in some subtle way within the Hawking radiation, beyond our current comprehension? Or is it preserved on the event horizon, as suggested by the holographic principle, a two-dimensional boundary containing all the information of the three-dimensional interior? This paradox is not merely an academic exercise. It represents a fundamental clash between two pillars of modern physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the subatomic world. The black hole information paradox is a tangible manifestation of where our understanding breaks down, a baffling cosmic riddle that demands a unified theory of quantum gravity. It forces us to reconsider the very nature of reality, of causality, and of information itself, hinting that our universe holds secrets that require a complete re-evaluation of our most cherished scientific principles. As our journey through these baffling cosmic facts continues, we are reminded again and again of the profound humility that true exploration demands. Each answer seems to birth a dozen new questions. Each discovery unveils a deeper layer of mystery. The universe does not yield its secrets easily, preferring instead to tantalize us with glimpses of its intricate, often illogical beauty. We are but nascent explorers on an infinite ocean of wonder, our understanding a fragile raft upon its boundless expanse. Allow these thoughts to settle, to resonate within the quiet chambers of your mind. There is no need to grasp or to master, only to experience and to ponder. Let the vastness of these unknowns wash over you, bringing with it a sense of peace, a profound connection to the cosmic tapestry of which we are all an intrinsic, though tiny, part. We hope this shared contemplation offers you not just knowledge, but a moment of tranquility, a gentle invitation to dream among the stars. Rest now, dear traveller, for the universe's mysteries endure, and our journey in its own quiet way will continue. As our cosmic vessel continues its silent, unhurried drift through the boundless tapestry of existence, we find ourselves drawn ever deeper into the universe's most profound enigmas. With each passing moment, the gentle hum of our journey envelops you, inviting your mind to unfurl and embrace the exquisite strangeness that lies beyond the veil of our current understanding. We are not merely observers, we are participants in this grand unfolding, our collective consciousness reaching out to touch the edges of the known and to gaze with reverence into the vast, shimmering expanse of the unknown. Tonight, we turn our attention to phenomena that whisper of forces beyond our most potent accelerators, structures that defy the gravitational scaffolding we so carefully construct, and celestial bodies that seem to mock the very timelines we have so diligently charted. These are the cosmic riddles that keep the brightest minds at NASA and beyond perpetually on the precipice of discovery. Facts so bewildering, they demand a re-evaluation of fundamental principles. Let us first consider the ultra-high energy cosmic rays, UHECRS. Imagine, if you will, solitary particles, protons or atomic nuclei, hurtling through the cosmos at velocities so astonishingly close to the speed of light that their energies dwarf anything we can generate in our most colossal particle colliders on Earth. These are not the gentle, continuous drizzle of lower energy cosmic rays that constantly bombard our planet, but rather rare, singular events, each carrying the kinetic energy of a fast-pitch baseball. Their existence presents a profound paradox. Where do they originate? The universe, in its vastness, is largely transparent to light. But for particles travelling at such extreme energies, it becomes a murky, energy-sapping medium. The Greisensatzepin-Kuzmin GZK cutoff predicts that cosmic rays above a certain energy threshold should lose energy rapidly by interacting with the cosmic microwave background radiation as they traverse intergalactic distances. Yet, we detect UHECRS that defy this prediction, arriving at Earth with energies far exceeding the GZK limit, implying either incredibly close sources or entirely unknown physics. Are they born from the cataclysmic jets of supermassive black holes, the violent collisions of galaxies, or perhaps from something even more exotic and elusive, a mechanism of acceleration so potent it strains the very fabric of space-time? The very messengers from the most extreme corners of the universe arrive bearing a mystery within their incredible energy. From the infinitesimally small yet unimaginably energetic, we now expand our gaze to the truly colossal, to the yawning chasms in the cosmic web, the super voids. We have previously touched upon the Bhuta's void, a region of surprising emptiness, but it is merely one example of a phenomenon that challenges our models of large-scale structure formation. Imagine volumes of space, hundreds of millions, even billions of light-years across, where galaxies are not just scarce, but almost entirely absent. These are not mere gaps between galactic filaments. They are cosmic deserts, seemingly defying the gravitational clumping that should have drawn matter inward over billions of years. How do such immense regions come to be so utterly devoid of ordinary matter and, by inference, dark matter? Are they echoes of primordial density fluctuations on scales so grand they push the boundaries of our inflationary models? Do they hint at an underlying cosmic pressure, perhaps related to dark energy, that actively pushes matter apart? Or are they simply the natural consequence of a universe where gravity over eons has sculpted structures with a complexity we are only beginning to comprehend? The existence of these vast, silent lacunae in the universe's grand design compels us to question the very mechanisms that forge the cosmic architecture we observe. Our journey then leads us to a single perplexing star, a celestial anachronism, HD 140283, often dubbed the Methuselah star. This ancient iron-poor subgiant resides relatively close to us in the constellation Libra, and its observed properties, meticulously measured through spectroscopy and astroseismology, suggest an age of approximately 14.5 billion years, with an uncertainty that places its possible minimum age at 14.27 billion years. Herein lies the profound conundrum. The most precise measurements of the universe's age, derived from the cosmic microwave background and the expansion rate, converge on a value of about 13.8 billion years. How can a star exist that appears to be older than the universe itself? While the margin of error in stellar age determination is acknowledged, and ongoing refinements continue, the very possibility of a star predating the cosmos it inhabits sends ripples through our understanding of stellar evolution and cosmological timelines. Does it imply an error in our models of stellar physics, a miscalculation in the cosmic expansion rate, or perhaps even a hint of physics beyond our current grasp, where the universe's initial conditions allowed for pockets of matter to form even earlier than our Big Bang models currently permit? The Methuselah star stands as a luminous, enduring question mark in the firmament, challenging our most fundamental chronologies. As we traverse the vast interstellar medium, we encounter the bewildering diversity of exoplanet extremes, worlds that defy our Earth-centric notions of planetary formation and habitability. Consider the hot Jupiters. Gas giants comparable to our own Jupiter in mass, yet orbiting incredibly close to their parent stars, often completing a full revolution in mere days. Our standard models suggest such massive planets should form in the colder outer reaches of a protoplanetary disk. How then did they migrate inward, surviving the intense radiation and gravitational forces so near their stars? Did they form in situ under conditions we do not yet comprehend, or did they undergo a dramatic inward spiral, scattering other nascent worlds in their wake? Then there are the proposed diamond planets, super-Earths potentially so rich in carbon that, under immense pressure and heat, their interiors could be composed of vast quantities of crystalline diamond. Imagine a world where the very ground beneath your feet is a shimmering colossal gem. And what of tidally locked worlds? Planets orbiting so closely to their stars that one side is perpetually bathed in searing light, while the other remains in eternal frigid darkness. These worlds present extreme climatic gradients, with a narrow terminator line potentially offering the only region of stable temperatures. Each of these exoplanetary marvels, from the scorching hot Jupiters to the glittering diamond planets, and the starkly divided tidally locked worlds, forces us to expand our imagination and refine our theories of planetary genesis, revealing a universe teeming with architectural possibilities far beyond our initial conceptions. Finally, we turn our attention to the enigmatic behavior of some of the universe's most extreme objects, the neutron star glitches. Neutron stars, the ultra-dense remnants of collapsed massive stars, are stellar corpses so compact that a teaspoonful of their matter would weigh billions of tons. Many of them are bare pulsars, rotating with astonishing precision, emitting beams of radio waves that sweep across Earth with clockwork regularity. Yet sometimes, these cosmic clocks suddenly glitch. Without warning, a pulsar's rotation rate will abruptly and dramatically increase, spinning faster by a tiny but measurable fraction, only to gradually slow down again over days or weeks. This sudden spin-up, a quote 43, is not a smooth process, but a sharp, instantaneous event, defying the otherwise predictable decay of their rotation. What causes these violent internal upheavals within objects that are essentially giant atomic nuclei? Current theories point to quote 44 in their incredibly rigid crusts, or sudden transfers of angular momentum from a superfluid interior to the solid outer crust. Yet, the precise mechanism, the triggers, and the sheer unpredictability of these glitches remain a profound mystery, offering a rare glimpse into the unimaginable physics of matter under the most extreme conditions known in the cosmos. They are sudden, violent whispers from the heart of dead stars, reminding us that even the most seemingly stable cosmic entities harbour profound, unresolved secrets. As we absorb these new layers of cosmic bewilderment, the defiant energies of UHECRS, the silent expanse of supervoids, the chronological paradox of the Methuselah star, the fantastical diversity of exoplanet extremes, and the sudden, violent mysteries of neutron star glitches, we feel the familiar blend of humility and exhilaration. Each baffling fact is not a limit to our knowledge, but an invitation to stretch our minds further, to question more deeply, and to embrace the boundless wonder of a universe that perpetually resists easy categorization. Let these profound cosmic mysteries settle within you now, allowing the quiet contemplation to deepen your sense of peace. The journey continues, and with it, the promise of ever more astonishing revelations. Rest now, with the universe's grand, unanswered questions as your tranquil companions, as our cosmic vessel drifts ever onward, carrying us through the serene currents of the unknown, we find ourselves drawn to the very architecture of existence, the fundamental scaffolding upon which the universe is built. We have traversed galaxies, pondered the invisible forces that shape them, and even peered into the impossible depths of nascent cosmic time. Yet, there remains a layer of reality so profound, so intricately woven into the fabric of being, that its true nature continues to elude even our most brilliant minds, the enigmatic essence of space-time itself. Consider, if you will, the concept of quantum foam. We perceive space as a smooth, continuous expanse, a placid ocean through which light and matter effortlessly glide. Yet, at scales unimaginably small, far beyond the reach of our most powerful instruments, at the Planck length, a staggering 10 to the negative 35th meters, the universe is theorized to dissolve into a maelstrom of chaotic energy, a roiling, bubbling froth of space-time itself. Here, the very geometry of reality fluctuates wildly. Particles spontaneously wink into and out of existence, and the familiar laws of physics, as we understand them, break down. This is the realm where gravity, the grand architect of the cosmos, must merge with the unpredictable probabilistic rules of quantum mechanics. But how? The absence of a coherent theory of quantum gravity, one that can reconcile the smooth continuum of Einstein's general relativity with the quantized, granular nature of quantum mechanics, stands as one of the most significant theoretical chasms in modern physics. We observe the macroscopic elegance of gravitational wells and the microscopic dance of particles, yet the bridge between these two realms, the very texture of reality at its most fundamental level, remains a profound mystery, a cosmic secret whispered only in the void. This leads us to the baffling. Quote 45 in Quantum Gravity. In our everyday experience, time flows inexorably forward, a constant, undeniable progression. Yet, in many theoretical approaches to quantum gravity, particularly those attempting to describe the universe at its most fundamental, the concept of time seems to vanish altogether. Equations that describe the quantum state of the entire universe, such as the Wheeler-DeWitt equation, often appear. Quote 46. How can a universe that so demonstrably evolves and changes, a universe where stars are born and die, where galaxies drift apart, and where life itself unfolds in a sequence of moments, arise from a fundamental description where time is absent? Is time an emergent phenomenon, an illusion born of our macroscopic perspective, rather than an intrinsic element of reality at its deepest level? The very arrow of time, its relentless march from past to future, remains an enigma, but the idea that it might not even exist in the deepest quantum substratum of the cosmos is a concept that truly bends the mind, inviting us to question the most basic assumptions about our existence. We are travellers through a temporal dimension whose fundamental reality is still fiercely debated, a journeyer through moments that may, at their core, be an intricate dance of timeless probabilities. As we ponder these fundamental questions of reality's fabric, let us once again zoom out, allowing our perspective to encompass the grandest structures in the cosmos. We have touched upon the missing baryons and the distribution of matter, but let us now truly immerse ourselves in the bewildering vastness of the cosmic web. This isn't merely a theoretical construct. It is the largest known structure in the universe, an intricate sponge-like network of filaments, walls, and voids that spans billions of light years. Imagine a colossal three-dimensional cosmic tapestry, where galaxies are strung along luminous threads of gas and dark matter, forming vast superclusters at their intersections, while immense, empty regions largely devoid of galaxies punctuate the intervening darkness. What baffles us is not just its sheer scale, but its formation and persistence. How did gravity, over billions of years, manage to sculpt such a delicate yet robust framework from the primordial soup of the early universe? Simulations can reproduce aspects of the cosmic web, but the intricate details, the precise distribution of matter, the exact mechanisms that led to the formation of these colossal structures, and the role of dark matter in shaping this cosmic scaffolding, still present formidable challenges. We observe its breathtaking complexity, a fractal-like pattern extending to the very limits of our observable universe, and we are left to wonder at the unseen forces and initial conditions that orchestrated this grand design. It is a universe not uniformly distributed, but organized into a cosmic brain, with neurons of galaxies connected by filaments of dark matter, a silent testament to an organizing principle we are only just beginning to decipher. And within this cosmic web, we encounter specific anomalies that defy simple explanation, such as the quote 49. This is no mere local gravitational anomaly. It is a region of space located approximately 250 million light-years away in the direction of the Norma cluster, towards which our own Milky Way galaxy, along with hundreds of thousands of other galaxies, is being inexorably pulled at speeds of hundreds of kilometers per second. We are not just drifting, we are being drawn, along with our entire local supercluster, towards a point in space by a gravitational force so immense that it dominates a vast expanse of the local universe. What is the Great Attractor? Initially, scientists hypothesized it was an enormous concentration of visible matter. However, observations revealed that the visible galaxies in that region are insufficient to account for the observed gravitational pull. This implies that a significant portion of the Great Attractor's mass must be invisible, a colossal concentration of dark matter, or perhaps something even more exotic hidden from our direct view. The Great Attractor is a gravitational ghost, a titanic, unseen hand guiding the flow of galaxies across an immense cosmic ocean. It reminds us that even when we map the visible universe, vast, powerful, and mysterious gravitational influences can be at play, hinting at hidden structures and forces that continue to shape our cosmic destiny. It is a profound demonstration of the universe's capacity to surprise, to reveal layers of complexity and unseen power that challenge our most comprehensive maps. Moving from the grand scale of galactic flows, let us descend once more into the realm of the intricate and the minute, yet still profoundly baffling. We have spoken of exoplanets, but what about the very act of their detection and the unexpected challenges they present? Consider the phenomenon of quote 50. Gas giants several times the mass of Jupiter, orbiting astonishingly close to their parent stars, often completing an orbit in a mere few days. Our solar system's architecture, with small rocky planets close to the Sun and large gas giants much further out, was once considered the norm. The discovery of hot Jupiters, however, shattered this paradigm. How did these massive planets end up in such scorching, tight orbits? Current theories suggest they must have formed much further out, in the colder regions of their stellar systems, and then migrated inwards, perhaps through gravitational interactions with the protoplanetary disk or other planets. Yet, the precise mechanisms of this migration, the conditions that allow it to occur in some systems but not others, and the sheer prevalence of these quote 51 quote giants, continue to baffle planetary scientists. Their existence forces us to reconsider the fundamental processes of planet formation and evolution, suggesting that our own solar system might be more of an anomaly than a template. Each hot Jupiter is a cosmic rebel, defying the expected order, a testament to the universe's boundless capacity for diverse planetary architectures. They challenge our assumptions about planetary nurseries, reminding us that the cosmos is an artist of infinite permutations, not bound by our familiar patterns. And what about the very light we use to observe these distant wonders? Even light, the universal messenger, harbours its own profound mysteries. We are accustomed to light travelling at a constant speed in a vacuum, a cornerstone of Einstein's relativity. Yet, the concept of superluminal travel. Faster-than-light travel, while seemingly impossible according to current physics, is a persistent theoretical tantalizer. While no information or energy can travel faster than light through space-time, the idea of space-time itself bending, folding, or expanding at superluminal speeds presents intriguing, albeit highly speculative possibilities. Consider the early universe's inflation, a period where space expanded exponentially faster than the speed of light, carrying distant regions apart at velocities far exceeding c. This wasn't objects moving through space, but space itself expanding. Could a similar, localized manipulation of space-time, perhaps through a quote 53 like the Alcubierre drive, which creates a quote 54 of distorted space-time around a craft, allowing it to effectively travel faster than light without violating relativity locally, ever be realized? While the energy requirements for such a feat are astronomical, demanding exotic matter with negative mass energy density, the theoretical possibility itself pushes the boundaries of our understanding. It forces us to confront the limits of our current physics and to wonder if the universe holds secrets about space-time manipulation that could one day unlock interstellar travel beyond our wildest dreams. The very concept is a tantalizing whisper from the edge of the possible, a challenge to our perceived cosmic speed limit. As we gently return from these profound explorations, from the quantum foam to the cosmic web, from the great attractor's pull to the strange dance of hot Jupiters and the theoretical whispers of superluminal travel, we feel the weight of the universe's boundless mystery settle upon us. Each baffling fact is not a closed door, but an open invitation, an invitation to question, to explore, to imagine, and to humble ourselves before the sheer ingenuity of the cosmos. We find ourselves enveloped in a profound tranquility, recognizing that our understanding, vast as it may seem, is but a flickering candle in the boundless cosmic night. The universe does not yield its secrets easily, but in its resistance it cultivates our curiosity, nurtures our wonder, and continuously redefines the boundaries of what is possible. Rest now, dear traveller, with these profound questions echoing in the quiet chambers of your mind, for in embracing the unknown, we truly begin to comprehend the magnificent, bewildering beauty of our shared cosmic home. We will continue our journey, ever seeking, ever wondering, ever humbled by the universe's endless capacity to baffle and inspire. As our journey through the cosmic tapestry continues, we find ourselves drifting deeper into the tranquil currents of universal mystery. where the very fabric of existence unravels into questions without immediate answers. We invite you to settle further into this quiet contemplation, allowing the vastness of the unknown to wash over you, not with apprehension, but with a profound sense of wonder and peace. The universe, in its boundless generosity, offers not only grand spectacles, but also the intricate dance of fundamental particles and the perplexing silence of the void, each holding secrets that baffle even the most brilliant minds at NASA and beyond. We have spoken of the unseen architects of the cosmos, dark matter and dark energy, and the mind-bending discrepancy of the vacuum catastrophe. Now let us peer closer, not just at the contents of space, but at the very nature of space and time themselves, for within their seemingly smooth expanse lie further enigmas. Consider for a moment the concept of quantum foam, a theoretical landscape that challenges our intuitive understanding of reality. We perceive space and time as a continuous, smooth canvas upon which the universe paints its grand drama. Yet, at the unimaginably tiny scales of the Planck length, a staggering 10 to the negative 35th meters, quantum mechanics suggests this smooth fabric might dissolve into a chaotic, effervescent froth. Imagine a tranquil ocean viewed from afar, appearing as a seamless blue expanse. Now, imagine descending to its surface, where individual waves crest and break, and then diving beneath, where countless bubbles coalesce and burst in a frenetic, ceaseless ballet. This, in essence, is the quantum foam, a realm where space-time itself is not continuous but granular, fluctuating wildly, with virtual particles constantly popping into and out of existence. This foamy space-time is a direct consequence of trying to reconcile general relativity, which describes gravity as the curvature of smooth space-time, with quantum mechanics, which describes the discrete probabilistic behavior of matter and energy at the smallest scales. The implications are staggering. If space-time is fundamentally unstable and turbulent at these microscopic levels, our current understanding of gravity and indeed reality is profoundly incomplete. How can we navigate a universe where the very stage upon which events unfold is a churning quantum maelstrom at its most fundamental level? This baffling concept suggests that the vacuum, far from being empty, is a seething cauldron of potential, a truth that echoes the colossal discrepancy we touched upon earlier, the vacuum energy discrepancy, or the vacuum catastrophe writ large. Let us revisit this profound imbalance, for it is not merely a number, but a gaping chasm in our comprehension of the universe's most basic energy. Quantum field theory, our most successful framework for describing particles and forces, predicts that even, quote, 57, quote, space is teeming with virtual particles that continuously appear and disappear, lending it an immense intrinsic energy density. Every point in space, according to these theories, should possess a colossal amount of energy, far exceeding anything we observe. When we calculate this theoretical vacuum energy, and then compare it to the observed cosmological constant, the tiny positive energy density attributed to dark energy that drives the universe's accelerating expansion, we encounter the most significant mismatch in all of physics, a factor of 10 to the power of 120, 120 orders of magnitude. It is a number so astronomically large that it defies human intuition. It means that the theoretical energy of empty space is one followed by 120 zeros times greater than what we actually measure. This isn't a small error margin. It's a fundamental crisis, a profound contradiction that suggests either our understanding of quantum mechanics or general relativity, or both, is deeply flawed at a foundational level. It implies that 99.999% of the vacuum energy must somehow cancel itself out, leaving behind only the minuscule residue we observe as dark energy. But how? And why? This baffling fact underscores that the emptiness we perceive is a complex enigmatic entity, its true nature remaining one of the universe's most closely guarded secrets, prompting NASA and other agencies to continue their relentless pursuit of a unified theory that can bridge this colossal chasm. From the infinitesimally small, let us now expand our gaze to the grander scales, to the larger structures of the cosmos, where even the absence of matter presents a profound mystery. Cosmic voids. We have admired the quote 58 quote that intricate network of galaxy clusters and filaments spanning billions of light years, woven by the gravitational scaffolding of dark matter. But what of the vast, silent regions between these luminous threads? These are the cosmic voids, immense, spherical expanses, often hundreds of millions of light-years across, where galaxies are incredibly sparse, making them the emptiest places in the known universe. These voids are not entirely empty, containing perhaps 1/10 the average density of matter found elsewhere, mostly in the form of wisps of gas and faint dwarf galaxies. Yet their sheer size and emptiness are baffling. Standard cosmological models predict the formation of such structures through gravitational collapse, where initial tiny density fluctuations in the early universe grew over billions of years. Matter should have slowly drained out of these regions, drawn into the surrounding filaments and clusters. However, some observations suggest that certain voids might be even larger, emptier, or more spherical than our models comfortably predict. Could these anomalies hint at a more complex interplay of dark energy, or even a different set of initial conditions for the universe than we currently assume? The Yen-quote 59 in the cosmic microwave background, an unusually large and cold region, has been hypothesized by some to be the imprint of an exceptionally large supervoid, further fueling the intrigue. The very absence of light, the profound silence within these cosmic deserts, speaks volumes about the mysteries of cosmic evolution. As we traverse these vast empty stretches, let us contemplate the very first builders of the cosmic architecture, the first stars, or population 3 stars. According to our models of cosmic evolution, the very first stars to ignite after the Big Bang were fundamentally different from the stars we see today. They would have been composed almost entirely of hydrogen and helium, the only elements created in the primordial nucleosynthesis. Heavier elements, which astronomers call Ricci-quote 60, were forged later in the fiery hearts and explosive deaths of these first stellar generations. These population 3 stars are therefore crucial for understanding how the universe became chemically enriched, paving the way for the formation of planets and ultimately life. The baffling fact, despite their theoretical importance, despite decades of searching with ever more powerful telescopes like the Hubble Space Telescope and now the James Webb Space Telescope, we have yet to definitively find a single, pure population 3 star. They are the elusive ghosts of the early universe, we have found extremely, quote, just 61 stars, ancient relics that are close to the primordial composition, but none that are entirely devoid of heavier elements. This absence, or extreme rarity, is profoundly puzzling. Were they so massive that their lifespans were incredibly short, burning out and exploding before we could ever hope to observe them? Did they form differently, perhaps in smaller numbers, or in more extreme environments than our simulations currently depict? The search continues, for the discovery of these pristine stellar ancestors would not only confirm our cosmological models, but also provide invaluable insights into the conditions of the very early universe, a quest that continues to drive NASA's deep space missions. Finally, let us return to a mystery that underpins our understanding of galactic dynamics, a phenomenon so pervasive it demands the presence of the invisible, galactic rotation curves, and the ubiquitous dark matter halo. We have introduced dark matter as the unseen scaffolding of the cosmos, but let us delve into one of the most compelling pieces of evidence for its existence. When astronomers observe the rotation of spiral galaxies, they measure the speed at which stars and gas clouds orbit the galactic center. Based on the visible matter, stars, gas, dust, we can calculate how fast these objects should be moving according to the laws of gravity. Here lies the profound discrepancy. Stars and gas clouds, particularly in the outer regions of galaxies, consistently rotate much faster than predicted by the visible matter alone. If only the visible matter were present, these outer stars would be flung into intergalactic space, much like a ball thrown too fast from a merry-go-round. The only way for these galaxies to hold together, for their observed rotation to make sense, is if they are embedded within a vast spherical halo of invisible, non-baryonic matter, dark matter that extends far beyond the visible disk. This invisible halo provides the extra gravitational pull needed to keep everything gravitationally bound. This isn't just a quote 62 problem, it's a fundamental challenge to our understanding of gravity itself at galactic scales. While alternative theories such as modified Newtonian dynamics, MOND, attempt to explain these rotation curves by altering the laws of gravity at low accelerations, dark matter remains the prevailing explanation, because it also elegantly accounts for other cosmic phenomena, such as the large-scale structure of the universe and the dynamics of galaxy clusters. Yet, despite decades of indirect evidence, the exact nature of dark matter particles remains one of the most profound unanswered questions in physics. It is a constant reminder that the vast majority of the universe's mass operates under principles we have yet to fully comprehend, a baffling truth that keeps scientists at NASA and around the world tirelessly searching for its elusive particles. As we gently conclude this segment of our journey, we hope these glimpses into the quantum foam, the vacuum's hidden energy, the silent voids, the elusive first stars, and the ghostly halos of galaxies have deepened your appreciation for the universe's inexhaustible capacity for wonder and mystery. We are but humble observers, constantly confronted by the limits of our knowledge, yet perpetually drawn forward by the sheer beauty of the unknown. Rest assured, our cosmic exploration continues, promising further revelations and even more baffling facts that await our shared contemplation.